Okay, so what we're going to do here is we're finally ready to start finding probabilities from the normal distribution. And what we're going to do in order to do that, we need to sometimes calculate something called a z-score. We may need to use a certain z-table in order to make some of these calculations, but we're definitely going to have to standardize. That's what it's called whenever you calculate a z-score. So standardizing is as simple as taking whatever the original value is from the normal distribution, subtracting off its mean and dividing by its standard deviation, sigma. Now you may then need to go look onto a z-table to find the area to the left under the curve of that z-score. In other words, find the probability of being less than that specific value. That's what we're going to end up doing here. So what I think would be best is if we worked on some of the homework assignments, actually. Some of the homework problems for this section, because this section really is just showing you a bunch of examples. That's really what it is, one of the rare cases. So why don't we pull some good examples from your homework itself? And I'll show you how you can use a z-table. So let's do this together. All right. So if you want, you can even open up your homework assignment and work it here with me for section 7.2. And that might just be pretty helpful there, Pilgrim. The notation z sub alpha. So alpha here is a subscript, is the z-score that the area under the normal curve to the right of z alpha is alpha. So what this means is this is the z-score that has an area underneath the curve to the right of it of whatever you want, alpha. So for instance, let me pull up my whiteboard here. For instance, if you had z sub 0.05, and that's a decimal right there, this is the z-score that has an area underneath the curve of 0.05 to the right of it. Well, what the heck does that mean? Well, let's draw a nice picture of our standard normal curve. There we go. Here we go. Now I'm going to draw the standard normal curve itself. Now bear with me because I am no artist. So it's going to be a rough drawing, and I think we're just going to have to live with that. That's not horrible for me. That's really not. This is the standard normal curve. Z sub 0.05, which would be maybe roughly this thing here. This is going to be the z-score that has 0.05 of the area to the right of it. That's what that means. Now, the problem is they use that notation, and I disagree with the notation because that says 0.05 of the area is to the right of it. But what we're going to see is all the z-scores we use talk about area to the left. So it's kind of a bit annoying that they have this kind of inconsistent symbology, but we're just going to have to deal with it. Okay, so let's get back to this. All right, so we've got a few questions it's asking us. Determine the area under the standard normal curve that lies to the left of, and now it's going to give us some z values. We're going to look at each one in its own case. Let me take off my jacket, it's warm in here. So the first z-score, we want the area to the left of z equals negative 1.54. We go to our table that is provided to us straight up in the homework assignment. What we're going to do is you can look up a z-score on the table, and it will tell you the area to the left of that z-score under the standard normal curve, which in this case is exactly what we're looking for. So we need to find negative 1.54. So here's how it works. You start by going out to your first decimal point in this column here. Then you go along and you find the second decimal point. So 0, 1, 2, 3, 4. All right. So we need negative 1.54. So here's the negative 1.5 row. This is negative 1.50, negative 1.51, negative 1.52, negative 1.53, and finally, negative 1.54 that we want. And so now the area to the left of a z-score of negative 1.54 is 0.0618. The reason we have to use a table in the first place is because the actual math behind it involves us using some high-level calculus and numerical analysis techniques that are frankly beyond the scope of this course. Well beyond the scope of the course. So we're just having to use a table here in the meantime. So the answer is going to be 0.0618, and we will be using this table many, many times. Next up, the area to the left of a z-score of negative 0.23. So once again, we need to look up negative 0.23. So let's see, z-score negative 0.2. All right, it's going to be along this row here. Negative 0.20, negative 0.21, negative 0.22. Negative 0.23, and we want the area to the left of that z-score. So I lost my place. The nice thing is, whenever you actually have a z-table in front of you, you're going to get one as a formula sheet for your next exam, and you're actually going to be able to see this top row of numbers here. It's going to be all in front of you. It's going to be a big, beautiful formula sheet. So the answer is going to be 0.409. So again, the z-score is negative 0.23. The area under the standard normal curve to the left of that z-score is 0.409. This is powerful because in the last section, the only thing we could do, we could only deal with z-scores that were related to one standard deviation away from the mean, 2 standard deviations, or 3 standard deviations using the empirical rule. But now using this z-chart, we can go out to 2 decimal points for a z-score. Because remember, the z-score represents the number of standard deviations away from the mean a given observation is. So a z-score of negative 1.21 means that the original underlying observation that had this z-score is 1.21 standard deviations below the mean. And I know it's below because the z-score is negative. All right, now we want the area to the left of a z-score of negative 1.21. So negative 1.2, this is negative 1.20, this is negative 1.21. It's going to be 0.1131. So z-scores can be negative, but the underlying probabilities must be positive because they're probabilities. Finally, we want the area to the left of z equals 0.82. So now we got to go find positive z-scores down here. 0.82, that's 0.80, 0.81. Here it is. The probability of being to the left of 0.82, a z-score, is 0.7939. So now That's great. Now we want the area to the right. What is it? Is it a to the right? Well, now for some reason they're splitting our z-charts into negative and positive z-scores. Okay. So first we want the area to the right of a z-score of 0.16. So we need to use the positive chart. Now the chart you get will be that original one that has negative and positive z values on it. But at any rate, we need to look up a z-score of 0.16, 0.16. So it's actually going to be 0.1, and then we go, here it is. So 0.16. But wait a minute. Hold your horses there, Pilgrim. Make it a little larger. 0.5636 is the probability of being to the left of, or the probability of being less than a z-score of 0.16. We want the probability of being to the right of it. We want the area to the right of it. But that's okay. We just need to make a little adjustment. So the area to the left of z equals 0.16. Well, we can read that from the chart. It's 0.5636. The area to the right of z equals 0.16 is, well, it's going to be 1 minus that. Because the chart is giving us this area here. It's giving us all this area down here below the z-score. What we want is actually this area here to the right of the z-score. Well, we know the total area under the curve is 1. So we can just subtract this area to the left from 1, and that's going to give us our area to the right. And so, oh boy, maybe I'll just do this one in my head. 0.4364. All right, I did that in my head, so take it with a grain of salt. Hey, I did it right in my head. We'll do a couple more examples of this. How about we do, well, let's just do this one as well. So now we want the area to the right of a z-score of 1.18. All right, so I'm going to rewrite this. 1.18 is now the z-score that we're going to look up. Oh. So just fixing all that. Next up, I'm going to go down here. I'm going to look up 1.18 as a z-score. All right, here's the 1.1 row. I need to go all the way out to the 1.18. I need to go out to 0.08 here. And here it is. .8810. So the probability of being to the left of a z-score of 1.18 is 0.8810. You can put a 0 before the decimal. So the probability of being to the right of it, we're going to need to subtract all. And once again, I'm on a streak, so let's see if I can do that one in my head. So the probability to the left of a z-score of 1.18 is 0.8810. The probability to the right of it, you have to do 1 minus. You have to use that complement rule. And that's going to give you 0.119. Assuming I didn't make a mistake, I didn't. We'll do one more example from this one. The area to the right of a z-score of negative 0.61. So we need to use this z-chart that has negative z-scores on it. Negative 0.61, that's negative 0.60. Here we go. Negative 0.61. The area to the left of negative 0.61 is 0.2709. Since we need the area to the right, we actually need to do 1 minus 0.2709, which is going to be 0.7291. 0.7291. So we're learning all kinds of fun stuff today. Now we can also find the area in between. We can find the area in between two z-scores. So take your standard normal curve. Take your standard normal curve. And let's say you want to find the area in between two z-scores. Let's say you want to find the area in between this z-score and this z-score, which would come out to being this area here. Shade this area. Yada, yada, yada. Well, think about it. We have a z-chart that tells us the probability, or it tells us the area under the curve to the left of any z-value you want, out to 2 decimal places. So if we look up this z-value on the z-chart, it would give us this area, but also all of this area down here. If we look up this z-value, it would just give us this area down here. So it turns out we're actually going to look up the probability for the larger z-value being to the left of it and subtract off the probability of being to the left of the smaller z-value here. That's what we're going to do. So using this system, the area that lies between a z-score of negative 1.13 and a z-score of positive 1.13, we're going to subtract the area to the left of z equals negative 1.13, the smaller one, from the area to the left of positive 1.13. We can use the chart in both cases. Give it a moment. So first we'll look up negative 1.13, negative 1.1, and then 0, 1, 2, 3. All right, it's going to be 0.1292. So the probability of being to the left of z equals negative 1.13 is 0.1292. We need to subtract that from the probability of being to the left of z equals positive 1.13. So 1.10, 1.11, 1.12, 1.13. So let me pull that up. So 1.13, it was 0.8707. Excuse me, 0.8708. And you get to use a calculator, so do I. So, yeah. And I have declared the answer shall be 0.7416. So you find the area in between by subtracting the smaller area from the larger one. And you can do this for multiple values. Maybe we'll do this one as well, just to give you a little extra practice. So the area between a z-score of negative 2.01 and a z-score of 0. Well, a z-score of 0 is interesting. 0 is going to be in the very center because 0 is going to be equal to the median here, which means I already know the probability of being to the left of 0 is exactly 0.5, 1/2. but we'll look it up on the chart for good measure. So we need to look up the probability being to the left of z equals negative 2.01. Negative 2.01, that'll be this guy right here. So we're subtracting 0.0222. Now we need to go look up 0 exactly. And when you look up a z-score of exactly 0, you get, like I predicted, 0.5 on the dot. Or 1/2. So we can do 0.5 minus 0.0222, 0.4778. So pretty interesting stuff. Now we're getting into the real gritty. So those first couple of problems we did, or the last three, I should say, what they did was they had us look up a specific z-score and find areas of the curve related to that z-score. Now it's the opposite. Now it wants us to find the z-score such that the area under the curve to the left of it is 0.52. What that means then is we're not going to look at 0.52 as a z-score. I'll even write that out here. 0.52 is not a z-score here. It's the probability of being less than a specific z-score. And we want to know what that z-score is. That is our goal. Thus, we're not looking up 0.52. Let me get rid of that. We're not looking up 0.52 as a z-value. What we're instead doing is we're looking for a 0.52 inside the table where the probabilities are hiding. And we want to get as close to 0.52 as we can. We're not going to get perfect all the time. Very rarely are you going to get perfect because some of the probabilities, oh look, 0.5199, that's about as close to 0.52 as we get. We go any bit to the left or any bit to the right, and we're just getting further away from 0.52. So this is as close to a probability of 0.52 as we're going to get. And now we need to figure out the z-score that corresponds to that. Well, it's going to be 0.0 and then 0, 1, 2, 3, 4, 5. So 0.05 is the z-score that has roughly 0.52 of the probability to the left of it, of the area under the curve to the left of it. And thus, that's our answer here. So you can look up a z-score, go find a probability. Or that's kind of like the direct method or the straightforward way. Or you can look up a probability and backtrack and find the z-score that corresponds to that probability. Now let's look at the next one. We want to find the approximate because we're probably not going to be able to get there perfectly. We want to find the z-score that is roughly has 0.32 of the area to the right of it. Oh, Josh, this means that we go, hey, you get back here, Mr. Table. Oh, we need to go look up 0.32 in the table. Oh, it's about right here. No. Read the wording carefully. We want, hey, where'd it go? We want the area in the right tail. We want the area of the right to be 0.32. This chart gives me areas to the left. See, it gives me areas to the left. That's okay. If the area to the right of our z-score is supposed to be 0.32, then the area to the left of our z-score will be, we're going to use the complement trick. And that's going to give us 1 minus 0.32 is 0.68. So we're not looking at 0.32 as a probability, we're looking at 0.68 because that's a left-tailed probability. That's the probability of being less than a specific z-value. So we're going to go look up 0.68 in the chart instead, or just get as close as we can to it. It's not going to be perfect, but it looks like right about here is it. This is a little further from 0.68. This is further from 0.68. So we're going to get, again, this is getting in the right ballpark. So about that. So that corresponds to a z-score of 0.40123456 0.47. Very good. So we're starting to rock, we're starting to roll, come out to the coast, we'll get together, have a few laughs. If you've ever seen Die Hard, that is a classic American film. All right, so we're rocking and rolling. Now we got to find the z-scores that separate the middle 63% of the distribution from the area in the tails. The tails are the side parts. Again, let's look at a picture. I think that would be most helpful. Now what we're doing, there's our Z1. This is going to be our Z2. And from the problem, it says we want the middle 63% of the data. So we want this shaded region here, shading. We want this to be 63% of the data, or expressed as a decimal, 0.63. We want 0.63 to be in the middle. Now, because of symmetry, Z1 and Z2 will have the same absolute value, but different signs, just meaning one will be the positive version of the other. Because it's symmetric, this is exactly 0.63 in the middle, and the normal curve is symmetric. So whatever this is, it's just going to have a negative sign slapped in front of whatever this is. Now, our chart is going to tell us the probability of being to the left of a specific value. So, first of all, if 0.63 is in the middle, that's going to leave 0.37 for the tails. In other words, this tail here and this tail here together will make up 37% or 0.37 of the data. There's two of them though. It's got to go into both of them. Because of symmetry, it's going to go into both of them equally. So we need to split our 0.37 into two pieces. Cut my tails in two pieces. And this is actually going to be our first resort. And if you do the math, that's going to be 0.185. So 0.185 of the area falls in here. .185 of the area falls in here. thanks to symmetry. So now we can go look up Z2. We can look up Z2, which is one of the Z-scores we need, by finding a probability of 0.185 and looking at the corresponding Z-score. So let's do it. We're going to go into our Z chart. We're going to get as close to 0.185 as we can as a probability inside the chart. And it's not going to be perfect. So let's see. 0.185. So this is 0.1867. That's not quite going to cut it. 0.1841. That's 9 units away. So yeah, that's going to be it. So negative 0.90. And remember, we can only get so close. This is about negative 0.9. Whoops. Because of symmetry, this would be about positive 0.9. And now it may reject our answer just because we may not have rounded the way it wanted. Nope, it was happy with that. Made a comma separated list and included both Z-scores. So this one's silly. Find the value of Z alpha. We want the value that has 0.05 of the data to the right of it, which actually means, because remember, this is just bad. This is bad terminology. I actually kind of hate this. But that means we want 0.95 to fall to the left of it. So we're going to go look up 0.95, or as close as we can get. It won't be perfect. Oh man, it's going to, both of these are equally close to 0.95. So that's about 1.64 or 1.65. We'll round to 1.65. This one is a little bit silly. Find the value of Z alpha. Alpha is 0.082. So in other words, find the Z score that has 0.082 of the area to the right of it. That's all that's saying. Alpha is the area to the right of it. It wants the Z score that has 0.082 of the area to the right of it. This is the same as the Z score, which has 1 minus 0.082, which is going to be 0.918 to the left of it. So we need to find the Z-score that has about 0.918 to the left of it, or rather we need to get as close to it as we can. So 0.918 to the left of it. Oh goodness, 0.9115, 0.9131. I'll go with this one. Well, wait, hold on. What am I saying? I'm totally off. Yeah, okay, I'm sorry. I was looking at the wrong decimal point. No, this would be it. 0.9177 is about as close to 0.918 as we can get. This one goes a little too high. So that is the probability of being to the left. The Z-score then would be 1.39 because that's all the way down there. Now we get into some interesting stuff. Now we get into some interesting territory. Now we're just told that a random variable x is normally distributed with a mean of 50 and a standard deviation of 7. So we are no longer being given z-scores. This is not a z-score. It's not saying z is equal to 50. No. It's saying it's a random variable that's normally distributed that has a mean of 50, standard deviation of 7. We are no longer being given z-scores. We are given x-scores that are normally distributed. These can be converted into z-scores. Why should we convert them? Because our tables are for z-scores only. That's it. We can't give you a table for every possible normal distribution. It wouldn't be practical. Oh, what about a mean of 27.3 and a standard deviation of 2.1? What about a mean of negative 37 and a standard deviation of 48.6? We can't do it. It's not practical to give you a table for every possible mean and standard deviation combination. So instead, what we're going to do is we're going to standardize. We need to standardize our x value, that is, convert it to a z-score. That's what we have to do. So first of all, we've already kind of looked at this formula. Now we're going to look at it even closer. Our z-score formula is x minus mu over sigma. This is going to be our formula for finding a z-score from a given x value. Well, in this particular case, let me move this over so I have more space. In this particular case, the x value of interest is 38. So it's going to be 38 minus mu, the mean is 50, divided by the standard deviation is 7. And now, when we standardize, that's going to end up with, well, I'll just do the math. It'll be negative 12 over 7. Now round that to 2 decimal places. So about negative 1.71. So we had to standardize so that we could use z-tables. So this is our z-score. Negative 1.71. We did all this calculation. The calculation is not really as bad as it looks. I have to write out every detail because I'm teaching it to you. I'm lecturing it to you. But in reality, it's not actually that bad. So I'm going to delete this. We're just going to remember that our z-score is negative 1.71. And now we'll answer a few questions. First of all, which of the following normal curve corresponds to the probability that x is greater than 38? In other words, you need a normal curve. It's going to be kind of hard to see. You need a normal curve that gives you the area to the right of an x value of 38. Now the mean is 50, so 50 belongs in the middle with Malcolm. It belongs right there in the center. But 38 is the value that you're going to be getting areas from. It says probability that x is greater than 38. Greater means to the right of. So we want this curve right here. This is the area under this curve. This blue shaded area is the probability of an x value greater than 38. Because remember, the area under the normal curve is both, it's going to be the probability in that region of the curve. And then it just straight up comes out and asks us, hey, what's the probability that x is greater than 38? Well, the probability that x is greater than 38, the probability that x is greater than 38 is the same as the probability that a z-score is greater than negative 1.71, because we calculated a z-score of negative 1.71 for an x value of 38. Thus, we need to find the area to the right of z equals negative 1.71. Remember, the chart will give you the area to the left of that z-score of negative 1.171. Goodness. So we need to use the complement rule. So returning to the chart, we need to look up negative 1.71, the z-score. It's going to be 0.0436. So let's see, negative 1.71, here you are, 0.0436. That's the probability associated with a z-score of negative 1.71. Then we do 1 minus 0.0436, because we actually want the area to the right of it. The chart is giving me the area to the left of it. The problem wants the area to the right of it. No worries, just use your 1 minus rule, and that's going to be 0.9564. Remember, we had to round our z-score to 2 decimal points because our z-table only goes out to 2 decimal points for z-scores. It goes out to 4 decimal points for probabilities, but only 2 decimal points for z-scores. And when I say we round it, it just means there's a chance that the area we're really getting is actually off by a little bit because of rounding error. But that's okay. Your MyLab's homework is designed to have a little bit of, they call it tolerance built in, where if you're a little bit off, if you're off by like 1% of the real answer, it's going to assume you knew what you were doing and there was just some kind of rounding issue. Let's see if we can find a more interesting problem. Okay, this one's interesting. But Josh, they're all interesting. They're about statistics. Yes, that is totally true. Thank you for telling me that. Okay, so now we still are talking about an X random variable. Thus, we're not talking about a z-score. If you're not talking about a z-score, it has to tell you what the mean and standard deviation are of that X value so that you can standardize the X values. You can figure out what the probabilities will be from a Z chart because you're going to standardize and get Z-scores. So let's just answer the first question. Assume that the random variable X normally distributed with mean 61 and standard deviation of 14. Compute the probability that X will be greater than 55 but less than or equal to 70. I'll give you a hint. For reasons that are going to go a little bit beyond what we really want to cover in mathematics, less than or equal to, or if you use greater than or equal to, is the same for the normal curve as just saying less than or greater than, respectively. In other words, the less than or equal to, forget about it. Don't worry about it. Don't let that trip you up because we're just going to assume it's the same as the less than. And that's only true for continuous distributions like this. The normal distribution is continuous. It's only going to be true for continuous distributions. If this was a discrete distribution, then no, we would concern ourselves with the or equal to. So basically, you can just pretend the or equal to isn't even there and that it's just another less than sign. Why? It has to do with the measure of real analysis, blah, 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 higher level hitting math than what we really want to get into at this time. So the first thing we can do is we can pick the chart that corresponds to that. We want the probability that X is basically between 55 and 70. So we need 55 and 70 to be on the chart, and we need to go and shade it. This one is a little bit silly because it looks like it could be this one or this one. The thing that's going to differentiate them, it looks so close, but look, the 55 is closer to the middle on this one. Here, the 70 is closer to the middle. So just think about it. If the middle is supposed to be 61, 55 is closer to 61 than 70 is close to 61. 55 is 6 units away from 61. 70, though, is 9 units away from 61. So it's going to be this one because the 55 is closer. And that's splitting hairs, like to a silly degree, because when you're just trying to think about these things, either of these charts is still helpful, even if this one isn't to scale perfectly, it's still helpful. So it is going to be that first one. And now we need to actually find the probabilities. So 55 and 70, we're probably not going to have a lot of space. So give me a moment. We'll take a picture of it. And we'll work this one out together on this whiteboard so we have more space. What we want is the probability, and I've already forgotten the numbers, so I'm glad I took a picture of it with my phone. We want the probability, this thing here, and what we know is that mu is about 61, or exactly 61. Sigma is 14. We know those things. So first things first, we need to standardize. We need to compute z-scores for each of our x values. We have to. We can't look 55 up on a chart because the chart is in terms of z. So our first z-score, the lower one, is going to be 55 minus 61 over 14. The next z-score is going to be 70 minus 61 over 14. According to the z formula. So 55 minus 61 is -6 divided by 14, round to 2 decimal points. That's going to give you z-scores of -0.43. This next one, 70 minus 61 is 9 divided by 14 and 0.64. So what we really want then is the probability of a z-score that is between -0.43 and +0.64. Now that we've standardized. This probability statement is essentially equivalent to this probability statement. So we find the area to the left of z equals -0.43 and subtract that from the area to the left of z equals 0.64. That is our process. So let's go back here. So we need to look up -0.43, -0.40, 1, 2, 3, okay. It's going to be 0.3336. And that's going to be the area we're subtracting. It's going to be the smaller area. the larger area, we need to then look up 0.64 on this chart. So let's see here. 0.64, it's going to be 0.7389. So then the calculation is going to be 0.7389 minus 0.3336. I'm just, again, going to use a calculator here because I'm a real American hero. 0.4053. And that's going to be our answer. And it should accept that because we had to fudge some of the numbers. Cornelius fudge. Let me go jump up and down. The light just came off in the room. It's because the light is motion censored and I have not moved much here. Okay, now this next one. The 86th percentile. Whoa! Oh! Assume a random variable x is normally distributed with a mean of 50 and a standard deviation of 7. Find the 86th percentile. What are you talking about? Well, what we want the x value that has 0.86 of the area underneath it. In other words, we want to go look up 0.86 as a probability in that table. If we look up 0.6 and find the corresponding z-score from the table, we're halfway there. Why are we only halfway there? Because we need it to be in the original x value. We then need to convert that z-score to an x value. Whoa. All right there, Pilgrim. Let's leave this up here. That's our directions, basically, our system, not of a down. So we need to go look up 0.86 as a probability in the table or get as close to it as we can. And that's going to be, come here, right about there. 0.8599 is as close as we can get. There you are. And that corresponds to a z-score of 1.01, 2, 3, 4, 5, 6, 7, 8. 1.08 is this z-score here. So here's what I can tell you. I can tell you the z-score is 1.08. Next, I need to use the z formula . But instead of plugging in x, I actually have a z-score and I need to solve for x. But that's okay. We know how to solve simple linear equations like that. It's going to end up being a simple linear. We're going to set 1.08, the z-score we found from the table, equal to x minus, mu is told to us to be 50, sigma is told to us to be 7. And now we can solve for x. We can multiply both sides by 7. We can also add 50 after we do the multiplication by 7. And so ultimately you're going to end up with x equals, we need to do 1.08 times 7 plus 50. Oh, and that's going to give us 7.56 plus 50, 57.56. And of course, you can use a calculator for that. You don't have to do it in your head. Okay, so you should be able to answer some of these using that reasoning. But we'll work one more together. I'll work this one. The mean incubation time of fertilized eggs is 19 days. Why do we care about this? This obviously isn't fertilized, human eggs that create children, because they don't incubate for 19 days. They, what the incubation period is like 9 months. So obviously we're not talking about human beings here. The mean incubation time of fertilized eggs is 19 days. Suppose the incubation times are approximately or roughly normally distributed with a standard deviation of 1 day. So we're going to assume the normal distribution here. In fact, in this entire section, you have to assume the normal distribution. If you don't, you can't use any of these analytics, any of these curves, any of this z-score business, because the z-score is inherently a standard normal distribution. So we have to assume the normal distribution. So even though it says approximately, don't let that throw you off. You're assuming a normal distribution all day on this one. We're going to assume a normal distribution with a mean of 19. It straight up tells us the mean is that. The standard deviation, sigma, is 1. It straight up tells us both of those pieces of information. And so now we need to determine the 13th percentile. So for part A here, we look up 0.13 as a probability and find the corresponding z-score for that. Then I'll be done here in just a little bit. Then we convert that z-score we get to an x-score. Kind of like the last problem we just did. So I'm going to go look on the chart for 0.13. Or as close as I can get to that, that's going to be maybe this one. No, that's 0.0, excuse me. 0.13, where are you? About right here. 0.1292 is actually closer to it. So 0.1292. That corresponds to a z-score of negative 1.13. Negative 1.13. So negative 1.13 is our z-score. We need to find the x-score for that, where mu is 19, sigma is 1. You solve for that, multiply both sides by 1, add 19. That's going to end up giving you 17.87, it looks like. It wants you to round to the nearest whole number, so round to 18. Finally, this one's going to be kind of tough, not really necessarily. The incubation times that make up the middle 95%. We need to go back to the standard normal curve and think about it for a second. Get ourselves a nice picture of the standard normal curve, something like that. We need the z-scores. This will be z2. This will be z1. We need this middle value, this middle amount, to be 0.95. We want the middle 95% of the data in there. But we're always thinking about things in terms of tails. We're always thinking about things in terms of tails. So if 0.95 of the data is in the middle there, then 1 minus 0.95 is 0.05. That 0.05. That leaves 0.05 to go in this tail and this tail. They get an equal claim to it. So then 0.05 divided by 2 equals 0.025. That means the area in this tail is each 0.025. Remember, whatever we get for this one, the positive z-score will just be the positive of that. So we go back to our table. We look up 0.025 as a probability inside the table. We're going to get, oh, it comes out exact. Very nice. That's a very famous value from the z-table. You're going to get a z-score of negative 1.96. The positive z-score would be positive 1.96. So this one will be negative 1.96. This one will be positive 1.96. And now we need to convert those back into X scores. This first one will be negative 1.96 equals X minus 19 over 1. So X is ultimately going to come out to 17.04. The second one, you're going to say positive 1.96 equals this. You solve for X appropriately, you're going to end up with 20.96. So 17.04 and 20.96 are going to be what does it here. And it wants us to round to the nearest whole number. So 17 to 21 days. 20.96 would round to 21. No. And we're done. Okay. That's a good place to quit.